Today we will discuss the moment of inertia, some more applications, and the moment of inertia of the different rigid bodies. Consider a solid sphere of mass capital M. This is a solid sphere, mass is capital M and radius is capital R. So it is going to be rotate about a axis diameter. Now our intention is to find out the moment of inertia of this solid sphere about this diameter. How to find out? Already we studied that the moment of inertia of a rigid body, how to write, already we discussed. I is equal to integration of dm into r square. That means in the rigid body we have to consider a element of mass is equal to dm. So what kind of the element that we are going to be choose here? You consider a disk of radius small r at a distance y from the center, and of course the width of the disk, the thickness of the disk take as dy. If you know the moment of inertia of that circular disk, then easily by integrating this equation we can find out the moment of inertia of the whole solid sphere. Then how to find out? Already we know that the moment of inertia of this circular disk about this axis, about its own axis, passing through the center and perpendicular to the plane. Already we know the formula, moment of inertia of the disk dm is equal to is nothing but, di is equal to is nothing but dm into r square by 2, where dm is the mass of the circular disk, r is the radius, and by 2. This is the already formula we derived for the circular disk about the own axis, moment of inertia is equal to mr square by 2. So simply I replaced capital M here with the mass of the disk small dm, and radius is equal to r square here and by 2. Now what is the moment of inertia of the whole sphere? Simply by integrating this equation we will get the answer. So integration I is equal to nothing but integration of dm r square by 2. Next only we have to find out the mass of the circular disk. Then easily by substituting that value in this equation we will get the moment of inertia of the solid sphere. How to find out the dm? Capital M is the total mass of the solid sphere. The mass is uniformly distributed throughout the volume. That means mass M is distributed throughout the volume, that is 4 by 3 pi r cube. And here we have to find out the mass of the disk dm. What is the volume of the disk? If you observe carefully, radius is small r and thickness is dy. So the volume of the disk simply can be written as pi r square into dy, thickness. Now what is the mass of the circular disk? Small dm is equal to, simply you will get mass per unit volume, that is 4 by 3 pi r cube into volume of the disk, that is equal to pi r square into dy. So pi will be gets cancelled here, you will get 3m by 4 r cube small r square dy. This is the mass of the disk. Now simply substitute this value in this equation. So that you will get 3 capital M by 4 r cube into r square dy and 2 also here. Now you will get this as 3m by 8 r cube will becomes outside, integration of small r square into dy. Here the radius of the disk is variable as well as this distance is also variable. So, in order to integrate that one should be converted into the other. How? Now, moment of inertia I is equal to of the solid sphere you got as 3m by 4r cube integration of r square, already one more r square is there. So, this will become r square power 4, r power 4 by 2 into dy, that is equal to 3m by 8r cube integration of r power 4 dy. And here small r is variable as well as the y is a variable. So, what we do here, we convert one into other. So, from the simple mathematics you can write capital R square is equal to is nothing but, from the figure, capital R square is equal to, we can write y square plus r square. That is r square is equal to, we can write capital R square minus y square. Substitute that in this equation. Now 3m by 8r cube integration of r square minus y square whole square into dy. Now the distance will be run from the here to here, that is minus y to minus r to capital R. These are the limits of this integration. Now this can be written as 3m by 8r cube into 2 into 0 to capital R. On expanding this equation, r square plus y square minus 2 r square y square. R square whole square means we will get r power 4 and y power 4 minus 2r square y square into dy. On integrating this equation, we will get the moment of inertia of the solid sphere about the diameter. That is 3m by 4r cube, and next r power 4 into dy integration. You will get r power 4 into y plus integration of y power 4 dy. You will get y power 5 by 5 minus 2r square. Integration of y square dy. You will get y cube by 3, where the limit runs from 0 to capital R. Now on substituting the limits, you will get the moment of inertia of the solid sphere about the diameter as 2 by 5 mr square. This is the moment of inertia of the solid sphere about the diameter. Consider a hollow sphere of mass capital M and the radius is equal to capital R. So it is going to be rotate about the axis diameter. Now my intention is to find out the moment of inertia about this axis. How to find out? And here important thing is the mass is distributed only throughout the area of the sphere. What is the area of the sphere? Already know, that is equal to 4 pi r square. Now here to find out the moment of inertia of this hollow sphere about that axis, and again I have to assume a small element. Here what kind of the element I am going to be assume here? Here I am going to assume a ring of radius is equal to small r. At a distance say y, and consider the thickness of this ring is equal to dy. Now my intention is to find out the moment of inertia of this, first of all this ring, and next by integrating that value simply we will get the moment of inertia of the hollow sphere. Then how to find out the moment of inertia of this ring? Already know the moment of inertia of a ring about its own axis, then nothing but passing through the center and normal to the plane of the ring. The formula is already know, I is equal to mr square, where r is equal to here radius. Using the same concept here, we will write the moment of inertia of that ring. What is the mass of the ring here? Say for example dm. Now the moment of inertia of this ring about this axis is equal to, we can write dA is equal to nothing but dm into r square. Then what is the moment of inertia of the whole sphere? Simply by integrating this equation we will get the answer. That is I is equal to integration of dm into r square. Then here we have to find out the mass of the ring. How to find out? You see here the total mass of the sphere only concentrated on the surface. So m is distributed on the area 4 pi r square. Then what is the mass of the ring? The mass of the ring is actually distributed along the circumference. So if you stretch that ring, you will get like this. Its length is equal to, you will get 2 pi r, and thickness here assumed that is how much? dy. So we can write 2 pi r into dy. Then what is the mass of the ring? dm is equal to, you can write mass per unit area 4 pi r square into 2 pi r into dy. So here pi will be gets cancelled 2. So you will get m by 2 r square into small r into dy. This is the mass of the ring. Now by substituting this value in that equation, we will find out the moment of inertia of the whole solid sphere. How? Now I is equal to, you will get integration of dm means we got just now capital M by 2 capital R square into R into dy, and along with that R square is there. So this we get as I is equal to m by 2 R square integration of R cube into dy. R cube into dy. So now how to convert? Again here R is variable and y also will be variable. One should be converted into the other. So to write the small r, you look here carefully. So it is going to be make an angle theta. This radius capital R is going to be make an angle theta. Then you can write here sin theta is equal to small r by capital R, or R is equal to, you can write capital R sin theta. And next, you observe carefully this circular ring. This is the circular ring what we assumed here. You see, this is already assumed as how much? Theta. Now the thickness is going to be make an angle d theta at the center of the sphere. Now as the thickness is equal to dy, already you know that we can write d theta is, dy is equal to r into d theta. That we have to substitute in this equation. So finally you will get I is equal to m by 2 r square integration of r cube means you can write r cube means capital R cube into sin cube theta. This is power, and next dy is equal to, you can write r d theta. That is equal to, you will get m by r cube and r, you will get r power 4, that is equal to m by 2 into r square. Now integration of sin cube theta d theta, where the limit will be runs from, you see, from here to here, that is 0 to pi. Next we have to integrate this equation. Then finally we can find out the moment of inertia of the sphere. Now finally we got I is equal to mr square by 2 integration of sin cube theta d theta, limits runs to 0 to pi. Now consider here x is equal to sin theta. Then you can write dx is equal to simply cos theta into d theta. Or you consider x is equal to here for the sake of easiness cos theta, then dx is equal to, you will get minus sin theta d theta. Now substitute that value in this equation. How? You see here mr square by 2 integration of 0 to pi sin square theta sin theta into d theta. We can write this equation like this. That is mr square by 2 into sin square theta means already you know 1 minus cos square theta into sin theta d theta. Now substitute these limits. X is equal to, I assumed as cos theta, then dx is equal to, I will get sin theta into d theta. Then I will get this is as mr square by 2 into integration of 0 to pi 1 minus x square, and sin theta d theta is equal to, you will get minus dx. Then you will write this as mr square by 2 integration of 0 to pi x square minus 1 into dx. Now let us integrate that equation. I is equal to, we got here mr square by 2 integration of 0 to pi x square minus 1 dx. Integration of x square minus 1, this is equal to x cube by 3 minus x 0 to pi. But what we assumed here, x is equal to, I assumed cos theta. So mr square by 2 cos cube theta by 3 minus cos theta 0 to pi. Now mr square by 2 cos pi cube pi by 3 minus cos pi minus cos cube 0 by 3 minus cos 0. Apply the value of cos pi and also cos 0 here, and upon simplification you will get the moment of inertia of the hollow sphere as 2 by 3 m r square. This is the moment of inertia of the hollow sphere about an axis, that is about the diameter, 2 by 3 m r square. Do remember here what we have for the solid sphere. Solid sphere is equal to, we got 2 by 5 m r square. For the same mass and also radius, the moment of inertia of the hollow sphere is equal to, you see here you get about some 0.67 m r square like that. But what about in the case of the solid sphere, you got 0.4 m r square like that. That means the moment of inertia of the hollow sphere will be larger than the moment of inertia of the solid sphere for the same mass and also same radius. Like that we can find out the moment of inertia of the different rigid bodies by taking the integration concept. Now next let us discuss the moment of inertia of the different rigid bodies when they are rotating with respect to the different axis, and the combination of the rigid bodies also we discuss here. And moreover, if you would like to find out the radius of gyration of the hollow sphere and also solid sphere also, that easily we can find out by looking at this equation. I is equal to, we know 2 by 3 m r square we got here. This can be simply written as mk square. Now by cancelling this m like this, and simply we can find out the radius of gyration of the hollow sphere about the diameter axis is equal to as 2 by 3 into capital R. In the same way, the moment of inertia of the solid sphere also, we got 2 by 5 m r square. So its radius of gyration simply will become root of 2 by 5 into capital R. So we will be in the position not only in finding the moment of inertia of the any rigid body about the different axis, but also we can find out the radius of gyration also. These are the two circular rings, each of mass is equal to capital M and the radius is equal to capital R. Now they are going to be rotate about an axis, This is the axis of rotation is given to you. Now we require to find out the moment of inertia of the ring about that axis. We already studied that in the system of the particles. Whenever the different kind of system of particles are given to you, the moment of inertia of the system of the particles simply can be written as I is equal to, here you can assume as the two particles. So you can write I1 plus I2. Now, actually ring is not a particle. Now we have to find out the moment of inertia of the each ring about that axis. What is that axis actually? If I consider the one ring, now this is the axis which is tangent to the what? A ring. Now we require to find out the moment of inertia of the one ring actually with respect to this axis. Already we know how to apply the parallel axis theorem. Whenever we have chosen a parallel axis which is passing through the center of mass, and whenever you know the moment of inertia of this ring about this axis, then easily we can find out the moment of inertia with respect to this axis. This value already we know, ICM is equal to mr square by 2, already we have studied. Now the moment of inertia about this axis will become, parallel axis will become ICM plus mr square. ICM means about this axis, parallel axis which is passing through the center of mass, and the axis is present in the plane of the ring, that already you know, mr square by 2 plus capital M, r is equal to the perpendicular distance between the two parallel axes, that is equal to capital R. So you will get 3 by 2 mr square. This is the moment of inertia of one ring about this axis. Now this axis is tangent to the both the rings itself. That means the moment of inertia of this ring with respect to this axis, and also with respect to the moment of inertia of the other ring with respect to the same axis, same. So simply this can be written as 2I1. So 2 into I1. I1 is equal to is nothing but this is the moment of inertia of the ring about this axis, that is equal to 3 by 2 mr square. 2 gets cancelled, and finally you will get I is equal to 3 mr square. So like this we can find out the moment of inertia of the different rigid bodies when they are combined. Let us take one more example. Two solid spheres are here. Each of radius capital R and each of mass is equal to capital M. Now we require to find out the moment of inertia about the diameter of the one of the spheres. With respect to this we have to find out. Then how to find out? Again very simple. These are the two bodies are there, number 1 and number 2. The moment of inertia about this axis is equal to simply will become I1 plus I2. So with respect to this I2, let us find out first of all. This axis is nothing but the diameter of the sphere, solid sphere here. What is the moment of inertia of the solid sphere? Already we have studied that is equal to 2 by 5 mr square. And next, we have to find out the moment of inertia of the first sphere about this axis. That means this is the first sphere, radius capital R. We have to find out the about this axis. Now again easily we can apply the parallel axis theorem to find out the moment of inertia of this solid sphere about this axis. With respect to the center of mass, if you take a parallel axis, now this distance will become, this is capital R, this is capital R. So total distance will become how much? 2R. Now the moment of inertia of this solid sphere about this axis is equal to, you will get I is equal to ICM plus mr square. ICM about its own axis, that is diameter, already we know, that is equal to 2 by 5 mr square plus capital M into The perpendicular distance between the two parallel axes, that already we know, 2r here, 2r whole square. So you will get 2 by 5 mr square plus 4 mr square. 2 by 5 mr square plus 4 mr square. 5 4 is 20, that is 22 mr square by 5. This is the moment of inertia of the first sphere. Let me call this is equal to I1. Then what is the total moment of inertia of that system about that given axis? I is equal to I1 plus I2. I1 means just now we got 22 by 5 mr square plus I2 means we got 2 by 5 mr square. On simplification, this is equal to, you will get 22 plus 2, that is equal to 24 by 5 mr square. Of course, if you are asked the radius of gyration about this axis, and simply we can find out, this may be equated as mk square, mm will be gets cancelled, k is equal to, you will get under root of 24 by 5 into r square. This is the way of finding the moment of inertia of the different rigid bodies when they are combined. Let us take the few more examples to find the moment of inertia. Here we will solve one problem. 4 spheres each of diameter 2a. Diameter is 2a means radius is given a, and mass m are placed with their centers on the 4 corners of a square of side B. Calculate the moment of inertia of the system about any side of the square. So that is the question here. 4 spheres are given, they are placed at the 4 corners of the square. The mass of each sphere is given small m to you, and the side of the square is given to you B, and the radius of the sphere is given to you A. Now we require to find out the moment of inertia about this axis. Simply again we can assume that there are the 4 particles. So moment of inertia of this system I is equal to nothing but I1 plus I2 plus I3 plus I4. Now let me call this is equal to 1, and this is equal to 2, and this is equal to 3, and this is equal to 4. Now the moment of inertia of the first sphere and also second sphere, both axes is actually only diameter, so moment of inertia also will be same. Let me call here I1 is equal to I2 is equal to I dash. And similarly about this axis, the moment of inertia of the third sphere and also fourth sphere are symmetrical. So let me call that is equal to I3 is equal to I4 is equal to I double dash. Now the moment of inertia of the system about that axis is equal to, simply we can write 2I dash plus 2I double dash R2 into I dash plus I double dash. Now we require to find out the I dash value as well as the I double dash value. I dash. I dash means what? It is the moment of inertia of the first sphere or the second sphere about that axis, that is nothing but further a diameter axis. What is I dash here? I dash is nothing but the moment of inertia of this spheres with respect to this axis is nothing but the diameter. About the diameter. About the diameter already you know the moment of inertia of the sphere. He did not mention whether it is a solid sphere or a hollow sphere. You assume it is as a solid sphere. So solid sphere means I dash is equal to already you know 2 by 5 mr square. Next we require to find out the I double dash. I double dash means what? It is the moment of inertia of the third particle as well as the fourth particle. Particle are nothing but here spheres. So about this axis we require to find out. And again we have to apply here parallel axis theorem. For this sphere, to find out the moment of inertia about this axis, now we assume a parallel axis which is passing through the center of mass. Now the moment of inertia of these spheres about this axis is nothing but I double dash ICM plus mr square. ICM about the own axis, that is equal to 2 by 5 mr square. And of course here the diameter of the sphere is given to a, that is radius is given small a to you, and hence 2 by 5 m a square plus, and here also a, plus m r square, m the mass of the body, into capital R. Here capital R, or you can say small r, which is equal to the perpendicular distance between the two parallel axes. Here the perpendicular distance between the two parallel axes is equal to b given, which is nothing but side of the square. So we can write mb square. Now I will write this is equal to as I double dash is equal to as 2 by 5 ma square plus mb square, or m is taken common, whether you take or not, nothing will be happen. Okay, leave off like this only. Now what is the total moment of inertia of the system about this axis, which is nothing but is equal to I is nothing but 2 into I dash plus I double dash. 2 into I dash means 2 by 5 ma square plus I double dash means 2 by 5 ma square plus mb square. So finally what you get? 2 into 4 by 5 ma square plus mb square. This is the answer for this question. In the same problem, we can choose the different kind of the axis also. How? You try yourself as a homework. Then what is the moment of inertia of the same system about this axis? At the time how to do? Just now we explained here about this axis. Again we are having 4 particles I1 plus I2 plus I3 plus I4, right, in the same way, and find out the moment of inertia of the each body with respect to this axis and find the moment of inertia. And of course you can take the one more axis also like this, about the diagonal of this square. Find out yourself the moment of inertia, again by writing the moment of inertia of this one, this one, this one and this one with respect to this axis, following the same kind of the method. Now you can find out the moment of inertia of this system about that axis also. And similarly, wherever maybe the different kind of the rigid bodies are given, simply by knowing the distribution or the presence of the different kind of the rigid bodies at the different places and with respect to the axis, easily we can find out. For example, if the same solid sphere are arranged like this. For example, if the same solid sphere are arranged at the 3 corners of a equilateral triangle of side A, and say each radius of the sphere is equal to small r, small r, small r, and depending upon the axis of rotation, we can find out the moment of inertia of this system also. You do yourself by taking this is as one axis, and do yourself taking this is as one axis, and taking the one more axis like this, that is which is passing through the center of this triangle and normal to the plane. And while solving the different kind of the problems, you will get the different kind of the situations where easily we can find out the moment of inertia with respect to the given axis following this method. From a disk of mass small m and radius small r, a circular portion of radius r by 3 is removed from the edges. Find the moment of inertia of the remaining system about a normal through the center of the original disk. Let us solve this. This is the disk, this is the center, and the radius of the disk is given to you capital R. So here we require to find out the moment of inertia of the remaining system about a normal through the center of the original disk. That is, this will become the axis. With respect to this axis, we require to find out. Now already from this disk, a circular portion of radius r by 3 is removed from the edges. You assume a small circular disk. This is small circular disk of radius is equal to r by 3. This is already removed. Then what will be left? Whenever this portion is removed, simply what will be left means and here nothing will be present. This is the center. Now we have to find out the moment of inertia of this remaining part with respect to this axis, which is passing to the center and normal to the plane. Now actually this can be find out by using this method. This is the original disk. Capital R is the radius, mass is small m. Of course, radius is given to you small r. Now with respect to this axis, already you know, the axis which is passing through the center and normal to the plane of the disk, already you know, mr square by 2. Now you choose the remaining part. This actually we have to find out with respect to this axis. Actually we don't know what is the mass of this one and what is the moment of inertia one. That is actually we have to find out. And you choose again this removed part here. This is the removed part. And say with respect to this axis, the moment of inertia of this portion plus the moment of inertia of this that left part, and that is obviously will become the total moment of inertia of the disk. And again here you see carefully, this is the total disk. From this total disk, this portion is removed. Then this will become. Now we require to find out the moment of inertia of this remaining part about this axis. For this, what we are going to do here, I have taken a full disk. We already know the moment of inertia of this full disk with respect to this axis. So that is exactly equal to the moment of inertia of the remaining part plus the moment of inertia of that removed part about the same axis. This is the axis. Say this axis we named as, the axis point is named as O. Now easily we can find out the moment of inertia of this one. How? We already know what is the moment of inertia of this one about this axis, that is passing through this center and normal to the plane, that is equal to already know mr square by 2. This actually we have to find out, say that is equal to I, which we require to find out, plus this moment of inertia, say that is equal to I dash. That means the moment of inertia of this removed part, if you find out with respect to this axis, then easily we can find out the moment of inertia of the remaining part by solving the equation mr square by 2 minus I dash. Then how to find out the moment of inertia of this one? The original mass of the disk is given to you small r, small m. Then what is the mass of this removed part? I will write here. Small m mass is there for the total area, that is equal to pi r square. Then what is the mass of this one? Say this is equal to, for example, m dash. M dash is there for how much area? The radius is already mentioned, that is equal to r by 3. That means pi into r by 3 whole square, that is equal to pi r square by 9. Then what will become the m dash? M dash is equal to is nothing but mass per unit area, that is pi r square into area of that removed part, that is equal to pi r square by 9. Then obviously the mass of the removed disk will become m by 9. Now with respect to this axis, what will become the moment of inertia? Very simple. For a disk about an axis passing through the center and normal to the plane, already we know the value. Now this axis simply will become the what? Parallel axis to this axis. So by applying the parallel axis theorem, we can find out the moment of inertia of this removed part about this axis, that is the value of I dash. Let me write the value of I dash here. I dash is equal to the moment of inertia of this removed part about this axis. I will apply the what theorem? Parallel axis theorem. ICM plus mr square. ICM. It is a parallel axis passing through the center of mass. For a circular disc passing through the center of mass and normal to the plane, already you know its value is equal to mr square by 2. But m means here what? M by 9. Next, what r square? R square is nothing but what here? R by 3 whole square by 2 plus. What is m here? M is nothing but the mass of this disc, that is equal to m by 9 into the perpendicular distance between the two parallel axes. This distance we require to find out. How much this distance will become? From this figure easily we can understand. The total radius, this is equal to small r. From the edge it is removed, so this will become r by 3. Then the distance between this center and also the center of the disc will become r minus r by 3. That is equal to, you will get 2r by 3. This is equal to, you will get 2r by 3. So what I have to write here? 2r by 3 whole square. On simplification of this one, you will get mr square by 18. So finally, we got the moment of inertia of this removed part about the axis O. Then substituting this value in this equation, easily we will get the moment of inertia of the remaining part about the axis which is passing through the center and also normal to the disc. So you will get mr square by 2 minus I dash is equal to, we got here mr square by 18, and finally you will get I dash is equal to, you will get 8 mr square by, you will get 18. This is the moment of inertia of the remaining part. How we solved this one? Check it once again. Here actually a disc is given to you, and from the disc a small disc is actually removed, and you are asked to find out the moment of inertia of the remaining part about the axis passing through the center and also normal to the plane. So that is actually asked. So we are doing like this. So this is the full disc. You know already the moment of inertia of this one. This actually, the total moment of inertia of this is actually is nothing but the moment of inertia of the removed part about this axis, as well as the moment of inertia of the, this is the left part, and the moment of inertia of the removed part about the same axis, O axis. That means we already studied that different particles when are given, the moment of inertia is equal to, simply can write I is equal to I1 plus I2 like that. And the same way we have done the same problem here. So the moment of inertia of this remaining part with respect to this axis plus the moment of inertia of the removed part about the same axis, which gives the total moment of inertia of the disc. This is the concept actually we have used. Now in the place of the disc, we can take a sphere or a square, and from that we can remove any kind of the part, and from that we can easily find out the moment of inertia of the remaining part with respect to the given axis. So this is very, very important problem, you practice once. Now we solve a simple problem here. The radius of gyration of a body about an axis passing through its center of mass is 24 centimeter given. Calculate the radius of gyration of the same body about a parallel axis passing through a point at a distance of 7 centimeter from its center of mass. A body is given, we don't know what kind of the body it is. If you take a axis passing through the center of mass, the radius of gyration with respect to this center of mass is given to you, k is equal to 24 centimeter. Now we require to find out the radius of gyration of the same body about a parallel axis. Let me take somewhere parallel axis like this. This is a parallel axis. This parallel axis is at a distance of how much? 7 centimeter from the center of mass. 7 centimeter. Now we require to find out the radius of gyration with respect to this center of, with respect to that axis, k dash we have to find out. How? You apply the just parallel axis theorem, we get the answer. Parallel axis theorem states what? I is equal to ICM plus EMR square. You know that already the moment of inertia of a body can be written as, of a rigid body can be written as mk square. And here k is equal to radius of gyration with respect to a axis passing through the center of mass. And similarly, moment of inertia of the same body about the parallel axis I is equal to, of course, moment of inertia changes as well as the radius of gyration also will be changes. K dash square, you call it K dash square, m K dash square plus m, or is equal to what here? It is a perpendicular distance between the two parallel axes, that is equal to 7 square. So mass will be gets cancelled. So finally you will get K dash square is equal to K square. The radius of gyration with respect to the center of mass is already given to you 24 square plus 7 square. Now if you simplify this one, this you will get as 625, that is K dash is equal to, you will get K dash square is equal to, you will get 625, K dash is equal to, you will get 25 centimeter. So like this we can find out the solution for this problem. So in this class we discussed already the moment of inertia of the rigid bodies, few rigid bodies, and basing on that we have solved the many problems. So basing on this concepts, you try to solve the problems related to the moment of inertia as you want.